Can you hear me? Yes. Okay. Hello, everyone. My name is Edoardo. I joined the DIGIMAN project in December 2021, and today I'm going to give you a brief summary of my work within the project, titled "Development of a Novel Smart Surface for Material Flow Handling." We are going to see a little bit of background, the design, simulation, and testing part, and finally some conclusions and next steps. Starting with the background, I'm going to talk about smart surfaces. What are smart surfaces? These are kind of non-prehensile system, as you can see in the animation, are flat surfaces that can manipulate material flow. In this case, is a trajectory tracking of a package. And the main characteristic are that they are programmable and modular, and these made this kind of system more flexible and efficient compared to the classic ones like conveyor belts or vibratory feeders. There are a lot of technologies that can be used for building these kind of systems. There is a list on the left part of the slide. I focused mainly on the last of the list, so the surfaces with rotors. And I noticed in the literature and among the existing systems that there are some things that can be simplified in this kind of class of system. For example, all these surfaces use a lot of motors, for example, at least two or three motors per module. And I thought this could be simplified in order to simplify the actuation and also the control. To do this is my proposal. So the idea is to build a modular surface like the previous system, but using idle rotors and not actuated rotors with a motor inside that makes the rotor spin. And this create a not actively driving surface that is exploiting external source for the object motion. For example, gravity inclining a surface, or of the object produced by conveyor belts before along the line. And for the manipulation part, the idea is to control only the direction of the axis of rotation of the instead of both the direction of the axis of rotation and the spinning of the wheel. Focusing on the single module, this is a schematic representation of the concept. So the idea is to have a spherical rotor supported by a shaped housing that permits its rotation in every direction. And this sphere is surrounded in its middle plane by some pins. And when I decide to define the axis of rotation of this sphere, I pushed a pair of opposite pins against the sphere, and this defines the axis. And as a normal rotor with its own mechanical axis, it creates some friction forces when an object passes on top of it, especially a parallel force along the axis direction and a perpendicular one, which is smaller perpendicular to the rotor axis. This is the final physical design, the 3D model of the design. So you can see the idle sphere in the middle on the left, and is surrounded by the pins which are placed inside coils or electromagnets. So the only actuation of this system is made by those coils. So the idea is when I want to define the axis of the sphere, I turn on a pair of opposite coils. They magnetize the pin inside, which is made of steel, so a ferromagnetic material. The pins are attracted to the sphere, which is steel, so ferromagnetic. And this contact defines the axis of rotation. When I want to change the axis, I turn off the coils and I turn on another pair. And the sphere is supported by another smaller spheres in order to be able to rotate in every direction. The second part of the work was about simulation. So I've done three main kind of simulations: a magnetostatic one with the software ANSYS and also Altair, then a dynamic simulation with Adams, and finally a simulation to evaluate the handling capability of the surface with the software MATLAB. And the objectives in this case were for the magnetostatic simulation to identify some parameters in order to improve the design. Then with Adams to verify the analytic model and also the functioning of the actual functioning of the system, and also then with MATLAB, but also Adams, the idea was also to evaluate their performances. Starting with the first simulation, so as I said, I simulated the sphere, the pin, and the coil in order to see which was the best shape of the pin in order to have the bigger force of attraction between the pin and the sphere. And with this, I was able to select the material, to define the proper design of the pin, and also to estimate the magnetic force, because you don't know the actual magnetic force in advance. Then moving on to the dynamic simulation, this was done of a single module. As you can see, the single sphere on the top right, and of a small surface to see if the functioning was really if the system was really functioning. And with the first single module, I've tested the analytic model that I proposed, and while with the surface, I've tested the functioning of the system, as I said before, and also I used this to validate the MATLAB simulation that I'm going to present in this slide. So in this case, what I've done was implementing the analytic model of these modules and of the surface on MATLAB and Simulink, and I use this to changing this MATLAB is more flexible to the changes. For example, I can change the layout and the arrangement of the modules in order to test different activities or tasks. Like, for example, in the animation, you see a trajectory, position tracking, or you can see the sorting and other activities. And with this system, I was able to evaluate the capability of the surface. And as I said, I've done a first evaluation of this simulation with Adams, with the dynamic simulation. Now, moving to the testing part, I've built first a prototype of a single module, and then of a small surface that you see on the picture on the right. So the idea was to measure the forces involved, to validate experimentally the models proposed, and then also the simulations. With the first prototype, I've done 3 main tests. With the first on the left, I measured the 2 main friction coefficients that were defining the analytic model. Then I've changed the direction of the axis compared to the object velocity in order to verify the analytic model. And finally, with the last test bench, I was measuring the magnetic force to see if the magnetostatic simulation was correct. Here are some results about the friction coefficient, the analytic model in the middle with the 2 friction forces, the parallel one, which is the bigger, the red one, and the blue one was the perpendicular one. And on the right, the magnetic forces measured. Now, moving to the small surface, what I've done was placing 12 of these modules and a camera on top of them in order to evaluate what was happening and measure what was happening with the camera. And this was used to experimentally validate the MATLAB simulation. So as you can see in the sorting done in the animation on the left, on the right instead is the reproduction of the movement of the object. And this was done in order to, as I said, to experimentally validate the movement of the package and then the MATLAB simulation. So in the left picture, you can see the magenta rectangle, which is the experimental movement of the package, and on the green one below is the simulated one. And as you can see, there is a good match between them. And I've done this changing the inclination of the surface, the type of the package, and other parameters. And this was used to have a quality check about the simulation of the MATLAB simulation of the system that is a sort of digital twin of the system. And finally, just other few examples about something that is more control related. With the camera, I was able to detect in real time which package was arriving on the surface, on the modules, and based on that, doing an activity. For example, on the left, you can see a sorting, which is a different distance along the modules line. For example, the white one was sorted after, and the red one is sorted before. While on the right animation, there is an orientation test. The red one that is coming now, supposed to rotate at about 45 degrees. Yes, while the one is rotating about 90 degrees. So I was controlling the orientation real time with the camera, and when the orientation was reached, the module stopped to produce the orientation, let's say. Then to conclude, what I presented was a modular surface in order to manipulate material flows. I investigated I've done simulations and prototypes and tests about it. And now I'm willing to improve, to have a bigger surface in order to test some more control-related tasks, for example, trajectory tracking or position tracking. And would also be nice to test the concept in an industrial environment with a big line. And that's all from my side. I would like to thank you all for your attention.